Speaker is Mr. Koki TERUI from JFE Steel Corporation in Japan. He is a senior researcher. He will be delivering his talk through the streaming option. And the title of his presentation is Investigating Carbon Neutralization in the DRI Process. So, Mr. Koki, please.
Thank you for introducing. I'm Koki TERUI from JFE Steel in Japan. Oh, cut. Okay. Today, my presentation title is Investigation of Carbon Neutralization of Direct Reduction Process by Applying Carbon Recycling. Next, please. This slide outlines the today's content. First, I'll explain about the background of this study. And next, a technical challenge for carbon neutrality. And third, I'll explain about the destination test planning. And finally, I'll explain about the construction plan for experimental shaft furnace. Next, please. First, I'll explain about the background of this study. Okay. This slide, this slide showed the JFE Steel's transition strategy to low carbon process. We considered the period up to 2030 to be a transition period, and we promote the transition to low carbon steel process. And the period from 2030 to 2050 is defined as the innovation period. We aim to achieve carbon neutrality by establishing and implementing innovative technologies. Please go back. Okay. We aim to reduce carbon dioxide emissions by 30% or more in 2030. And next, in 2050, we aim full carbon neutrality. And to achieve these challenging goals, the following technologies will be developed in our company. First, the use of the conventional blast furnace combined with the carbon recycling process. And the next, the use of the direct reduction method. And the third, the use of the electric arc furnace and the expansion of the use of the scrap material. And today, I'd like to explain about the direct reduction technologies as today's topic. Next, please. Next, please. Okay. Yes, in this slide, the two figures on the left represent the concepts of the conventional iron making process, the blast furnace method, and the direct reduction method. We are trying to incorporate carbon recycling process into this conventional iron making process. The targets are carbon in the blast furnace gas in the blast furnace method and the carbon in the top gas of the shaft furnace in the direct reduction method. As introduced in the previous presentation by Dr. Kashihara, JFE Steel is proposing carbon recycling blast furnace that capturing carbon dioxide from the blast furnace top gas and synthesize them and inject it into the blast furnace again, and carbon is recycling. Now, similarly, we now propose carbon recycling shaft furnace combining carbon recycling process with a conventional or direct reduction method. The following slides explain the concept of this process. Next, please. Okay, next, I'll explain about the technical challenges for carbon neutrality. Okay. JFE Steel plans to develop carbon recycling direct reduction steel making. The right figure shows the outline of the carbon recycling shaft furnace. The features of this process are first indirect use of hydrogen through neutralisation, and next, circulation of carbon within the process, and third, overcoming the endothermic effects of hydrogen reduction. In this process, methane is obtained by reacting carbon monoxide and carbon dioxide in the top gas with green hydrogen, and regenerated methane is injected into the furnace or reformed into carbon monoxide and hydrogen before being blown into the furnace. And the carbon is not discharged out of the system and circulates in the system. And hydrogen is supplied from the outside, and only water is discharged out of the system. Next, please. As you know, reduction with hydrogen is a highly endothermic reaction, but in this process, carbon is not discharged out of the system. Carbon continues to remain in the reducing gas as carbon monoxide, and there is no need to increase the hydrogen ratio in the reducing gas. The aim of the carbon recycling is to achieve carbon neutrality by repeatedly reusing carbon. And because reaction by carbon monoxide is an exothermic reaction, it is considered possible to avoid the endothermic effects of hydrogen reduction, such as a decrease in reaction rate or reaction degradation of iron laterite. This is explained on the next slide. Okay. This slide describes the various subjects of endothermic reactions. As I have said many times before, reduction by hydrogens involves a large endotherm, and reaction rate will decrease, and there is a concern that lowering of the reaction rate will cause a decrease in productivity of shaft furnace. And also, as I mentioned before, there is concern that the decrease in temperature and some may promote the reduction degradation of iron ore pellets. And in this photograph, the reduction test was carried out under the conditions of 82 by CO of 4.0, and the tumbling test was performed on the sample after the reduction. As you can see, the strength of the released sample decreases and fine powder is generated. So it is expected that the use of low-grade pellets will increase in the future, and we think that such low-grade pellets are likely to occur reduction degradation. But if this process which the hydrogen ratio in the reducing gas does not increase, it is thought that it is possible to minimize the occurrence of reduction degradation. Next, please. Yes. And next slide. Please go back. Please go. Sorry. Yes. Sorry. Thank you. And in this slide, this slide shows the effect of increasing the hydrogen ratio in the reducing gas on the distribution with the reduction degree in the shaft furnace. And this is an example of numerical simulating the reaction behavior in a furnace. The composition of the reaction gas is assumed for 82 by CO of 1.7 and 3.7. And the center figure shows the calculated distribution of reduction degree. And in this example, it is shown that the reduction in the reactor is delayed by increasing the hydrogen ratio, and the reduction degree in the center is lower, and this tendency becomes more significant when the hydrogen content in the reducing gas increases. And by increasing the hydrogen ratio in the reducing gas, the low reduction area is expanded at upper part of furnace. Because reduction degradation occur in the lower reduction region, it is assumed that reduction degradation is likely to occur when the hydrogen concentration increases. For these reasons, we thought that endothermic reactions should be avoided as much as possible. Please next. And next, I will explain about the methanation test planning. Yes. This page outlined the proposed methanation test equipment. Methanation needs the reaction of carbon monoxide or carbon dioxide with hydrogen using catalysis to form methane and water. And methanation is recognized as one of the important CCU technologies for achieving carbon neutrality in Japan. Methanation consists of these two reactions. Reaction of CO2 with hydrogen and CO with hydrogen. Both are exothermic reactions, so gas cooling is required. And recovering of waste heat generated by the reaction is also important. After the production of the methane, the moisture in the gas is removed by cooling. We plan to investigate the reaction behavior of hydrogen in catalyst bed using gas, simulating the ratio of carbon monoxide and carbon dioxide in the top gas of a shaft furnace. And we are considering proposing appropriate reaction conditions and optimizing the configuration of the reactor as development elements. Next, please. Okay. This page explains the specific issues related to the investigation of methanation. In order to establish the carbon recycling shaft furnace process, we plan to investigate the effects of gas composition, CO2 and CO ratio, and the amount of water addition on methanation reaction efficiency. The composition of the top gas of shaft furnace varies depending on the operating conditions and the quality of the raw material. So it is necessary to determine the appropriate amount of gas circulation and gas distribution in process. And in addition, depending on the condition of the methanation, a carbon may deposit on the surface of the catalysis and reaction efficiency will decrease. So appropriate amount of water is also added to avoid this. The right figure shows the schematic diagram of experimental apparatus of methanation test. In the experimental system, two methanation reactors were installed. The experimental conditions are shown upper part. We plan to test the reaction efficiency when the ratio of carbon dioxide to carbon monoxide is changed and the effect of the addition of water. And the catalysis is a nickel-based alloy, and methanation is operated under high pressure. And by using this experimental system, the good operating conditions will be proposed, assuming that the shaft furnace is equipped with methanation process. Next, please. No, okay. Finally, I'll explain about construction plan for experimental shaft furnace. Okay. JFE Steel plans to construct an experimental shaft furnace at East Works in our company in order to evaluate the effect of conditions such as composition and temperature of reducing gas and the quality of the raw materials and separation of the shaft furnace. Construction site is shown here near Tokyo, and DRI is produced at a standard rate of 0.5 ton per day. We can change the combustion of reducing gas for a wider range, and the pressure within the furnace also can be varied. After the start of operation of this equipment, the influence of the reducing gas conditions on the productivity and reduction degradation that may occur when using low-grade pellets were investigated from 2024. Next, please. Finally, this slide outlines the summary of my presentation. JFE Steel plans to develop carbon recycling direct reduction steelmaking, and in order to establish the carbon recycling shaft furnace, we plan to investigate the effects of gas composition and water addition amount on the methanation reaction efficiency. And bench scale test furnace will be built at JFE Steel's East Japan Works, and the testing is scheduled to begin in 2024. Next, please. That's all. Thank you.
Thank you very much, Mr. Terui, for your presentation. We have some few minutes for questions from the audience. Yes, and we have one there.
Thank you. The pilot plant looks very big. What is the capacity of this pilot plant? And I have seen in the picture that there's a reformer. Do you build a pilot plant for the matrix process, or is there, and the hydrogen is coming from containers? Why don't you build an electrolyzer for the hydrogen production?
Your question is the capacity?
What is the capacity of the pilot plant? Yes. Is this a matrix process? And the third question, for the hydrogen production, do you think to build an electrolyzer plant, or from where you get the hydrogen?
Your question is carbon monoxide and hydrogen is how do
you produce the hydrogen? Yes, the second question. And the third question, this is a direct reduction shaft with a reformer, so you build a matrix plant.
Hydrogen and carbon monoxide is generated by reforming of natural gas.
Okay, what is the CO2 advantage when you do the hydrogen production by reforming of natural gas?
Hydrogen production. Now, by reforming of natural gas. Okay, so sorry. Sorry, I can't.
One of the questions, Mr. Terui, one of the questions was if the plant will be built with the matrix technology, because it seems it has a reformer. Can you understand the question?
Your question is, sorry, please again.
What will be the technology for the direct reduction pilot plant?
Pilot plant technologies?
Yes.
Oh, no, not matrix technologies.
will have a reformer.
In our company's construction.
Will be on your own. Okay. Well. Any other question? Just the last, please. One more. Mm-hmm.
Thank you. I have a question that's come in online from Mr. Lin. In fact, two questions. First question, what is the flow rate of CO2 and hydrogen in the experiments and the amount of catalyst?
Oh, sorry, I can't answer your question. Sorry.
Okay.
I can't answer significant value. Sorry.
Okay. All right. Thank you.
Okay. Then we thank you, Mr. TERUI, for your presentation again. Thank you.
Thank you.
Next talk will come from tomorrow's session today because we had some cancellations. I invite to Dr. Hany HAMED. He is a manager for research and development at Emirates Steel Arkan. The title of his presentation is A New Approach for Efficient Hydrogen Generation, Increasing Pellet Use Ratio, and Development of HBI Direct Usage for Blast Furnace. Thank you.
Thank you. Thank you. Thank you. Thank you. Assalamu alaikum and good afternoon, everyone. Just before I start, I want to have a short video about Emirates Steel. If you can play this video, please.
Here in the United Arab Emirates, we embrace the vision of our leaders to remain persistent in our commitment to sustainability, guided by their vision and fortified by 25 years of excellence in the steel industry. Emirates Steel Arkan is not just decarbonizing the industry, we're reshaping the future of building solutions. Through harnessing innovative solutions, armed with profound expertise in recycling and electric arc furnace technology, we are a trusted low-carbon steel supplier to over 70 markets around the world. We are the first steel company to globally employ carbon capture technology, sourcing most of our electricity needs through clean energy. We achieved a certified CO2 intensity of less than half the global steel industry average. We stand at the forefront of clean technology adoption, pioneering the use of clean hydrogen to produce green steel, fostering partnerships to make Abu Dhabi a global hub for the green steel industry, empowering our customers with cutting-edge steel and building materials. We catalyze a substantial reduction in their carbon footprint. We are resolute in our commitment to environmental conservation, supply chain sustainability, and the integration of renewable energy. Our pledge is bold. A 40% reduction in carbon emissions by 2030, with the primary aim of achieving a net zero by 2050. Emirates Steel Arkan. Sustainable decision. Sustainable future. Sustainable future.
I want to start by saying that we have to look to the future about the green hydrogen and how we produce green hydrogen from the point of view of energy, which is a very important topic. So the title of this presentation is A New Approach for Efficient Hydrogen Power Supply. So I want to say one thing here, that we want to have a new concept of green, all green. We know exactly what is green hydrogen. And if we produce a green hydrogen from renewable energy, we call it green. But what about the green process and green load, which is a new topic here? So as you can see that the electric arc furnace, we consider it, sorry for the word, and from electrical point of view, is a very dirty load. That means that it is not friendly to the grid and introduce too much challenges to grid. And so how to convert the load into green? Because the conventional methods now to using the transformers that need additional effort to make the electric arc furnace green. And what is green here? How we can say electric arc furnace is green? Is it only because we can replace the natural gas by hydrogen? Or the green must have a more concept than only the hydrogen, which is going now, or low emissions? We have to introduce energy here also as one of the factors. So conventionally, this is not the conventional one, this is the future one. If we are talking about the electric arc furnace, which should be supplied from a different source of power converters. It's not like a transformer, traditional transformers. The power converters here, we talk about the power electronics or a device that convert the energy to match from the grid into the electric arc furnace. And so, if you are talking about the future of supplying the electric arc furnace by power converters, what does it mean? And if you can see also the electrolyzer, if it is integrated into the DRP process, it must be also supplied from a power converter. There's a two difference between the power converter for electric arc furnace and the power converter for the electrolyzer. What's the differences? And what is the consideration we have to take when selecting or scaling up the electrolyzer? Everybody is asking about what is the capacity for electrolyzer? Is it matching 100%, replacing the natural gas? What we have to consider when we scale up a pilot and as an electrolyzer pilot to scale it up to the, we can say, to high percentage of blending with the natural gas. So usually, the concept here is, we call it a microgrid concept. And it will be explained later on in the next slides. But just I want you to know that exactly that we have a similarity between arc furnace and electrolyzer in terms of the power electronics or power converter. Call it twin now. So the conventional system of the supplying the electrolyzer is simply, I use the grid or renewable energy to convert from AC to DC, and because the electrolyzer need a DC power supply and variable rate, so I have to have a variable DC-DC converters, we call it power converters. So the all green design, what we are talking about, it should also take care about the grid side. Now we are going to connect the electrolyzer to the grid, which is internal grid for the steel plant. And it can poses really bad effect on the grid, on the neighborhood. We can say about the neighborhood is similar to other plants which is connected to the same bus bar. And so we have to be sure that the electrolyzer, when it scale it up, is not introduce too much trouble to the grid itself. So from the grid side, as we can say, there is some parameters we need to take care about it. It's so electrical things like the total harmonic distortion and all of the things. Power engineers know exactly these terminologies. The power converter here, which we are talking about, it should have some feature like scalability. It can be scaled up. And fast power response, which is very important because maybe we need to have fast acting. Like now we're talking about a power converter, like similar, what we should supply the electric arc furnace, we have to supply also the electrolyzer if it is inside the plant itself. So it must be fast and also the voltage should be stable for increasing the lifetime of the electrolyzer itself. And there is something about the current and dynamic response. And there is also some consideration when you select an electrolyzer to match all this system. We have to take care about the maximum voltage to the electrolyzer and also the cell voltage. We have to keep it within certain limit, and also the current density for the stack. To have a system or power converter system that take care about all of that from the grid side to the electrolyzer side, it is not an easy task, because conventional power supplies we're going to see now, they don't consider really the future. So this is the conventional one you can find in the market. If you find electrolyzer, they provide this kind of power supply. Conventional one, we call it the terrestrial controlled rectifiers. And because it introduced some challenge or some disturbance to the grid, they added harmonic filters. We know exactly to filter the harmonics. So an additional capex we need to add. And sometimes because of the reactive power, we add the STATCOM or the SVC. Everybody knows about SVC for the electric arc furnace. Maybe we need to add also an SVC for a scaled up electrolyzer for the reactive power even. And so you can see that the conventional solutions, all negative from the electrolyzer side and the grid side and the power converter side. So this will not going to work for the future. So if we want to design the power supply for our power converter for the electrolyzer, we have to consider these three facts. The grid side, to take care about the grid side, and what about the power converter itself? So from the grid side, we have to ensure the quality of the power supply, or the effect of the electrolyzer to the grid itself. Have to be you can say that it should be friendly to be connected to grid. And so also, from the power converter, it need to be fast, and maybe we need to add some new feature to that power supply, which is bidirectional. Bidirectional for the power supply or power converter, it means that it can supply the active power and also can supply the reactive power to the grid. It's very important. So here the concept like the electrolyzer power supply should also act as a STATCOM or SVC at the same time. It means that maybe we don't need to have SVC anymore. And the electrolyzer itself, it has some characteristics that we have to follow, and mainly the fast dynamic response for supplying the power demanded to the electrolyzer. So we are focusing here on the power supply. Yes, what is the cost of power supply for the total electrolyzer system? As you can see, the BEM electrolyzer cost can be broken down into two main parts. I care only about 55% for the power supply, and among 55%, I have only 50%. That is the cost of the power supply. It was really to invest on the power supply for the electrolyzer because of what we can see for the future. So we propose a system that can tackle all these issues, from the grid side to the converter side, the power converter side, and to electrolyzer also. So this system actually, or the power converter system, which the two green one, AC-DC, DC-DC, we call it the multi-level neutral point clamped converter. This is a proposed topology for the electrolyzer power converter, and also for supplying the electric arc furnace. I know there is in the market really, some companies supply the arc furnace with the MBC converters. They are not using anymore a transformer, the conventional one, tap changer, SVC, STATCOM, increasing the efficiency for the electric arc furnace between 10 to 15%, reducing the energy, what I mean. So we have to find a unified power converter that can fit well with the electric arc furnace and the electrolyzer for the future. And I will go now to maybe some details, but I will not stress so much on the electrical details here. And so this is the design for, proposed design for that power converters. It starts from the medium voltage, which we connect usually the electric arc furnace, for example, to 33 kV, or the electrolyzer to 11 kilovolt. And so the power converter, what we are talking about is, we call it multi-level MBC converter. And this multi-level MBC converter is able to boost up the voltage and maintain the voltage and quality of the DC voltage with one of the methods we also propose it, which we call it direct power control, because we are talking about power, and it's a time to directly control the power, not to control the power indirectly. And we have in Emirates Steel, we have a patent in direct power control method. We register it in USA. And also from the other side, the electrolyzer side, we propose also another converter. We call it isolated bridge DC-DC converter. Isolated one. We select the isolated one because we can scale it up, the voltage up, adding more electrolyzer by scaling up the transformer, which is at the right side here. So the scalability also here is guaranteed, and the power quality, because it is multi-level, a topology is guaranteed here. Just here is some of the simulation, real-time simulation for the system itself. Here is electrolyzer response from, we select 1 megawatt electrolyzer to test. So we can see that the demand for electrolyzer, if we see the x-axis at the time, y-axis for the power, you can see that we can supply the electrolyzer from 100 kilowatt into full scale 1 megawatt in less than 1 second. And it's very stable without any overshoots. That means that the supply, the control is really dynamic response is very fast for that one. If we monitor the stack also voltage, we need not to exceed the voltage which is defined, and we define the stack voltage is should be defined by the maximum cell voltage, which shouldn't go more than 2 voltage. So you have number of cells, you have to design it, and the total voltage of the stack should follow that regime. Also the stack current, as you can see, that the current for the stack, for the full power, we can reach full power less than 1 second. Actually, it is 500 milliseconds. We can reach the full power. That is thanks to the new method of direct power control. Now we go for the stack itself. Why we focus on the stack? Because the lifetime, if I'm supplying the stack with voltage which is not stable, the lifetime for the stack will go down. So as we can see here for the left side, the stack voltage never exceeds 2 voltage, which is the limit, and also the current density not exceeding 3 ampere per centimeter square, which ensure the lifetime of the electrolyzer will be prolonged. If we go to the grid side now to see how the converter become green and the load now become green, everyone knows about the total harmonic distortion. This is one of the factors we have to take care about. It's very low, nothing. We see in the left side the power factor, which is unity. It means I don't need any more the SVC or capacitor or harmonic filters. No need for that. Efficiency for the power electronics is more than 96%. The converter side, the overall system efficiency is more than 90%, 92%. Electrolyzer plus the power system plus the transformer plus everything. You can see the downside is this is very important, this DC link or the voltage on the electrolyzer. We can see that it is, when we load it, suddenly it only go for 4.5% less than the nominal one. but it recovers in 400 milliseconds. Is very, very fast response for the electrolyzer. So how we can integrate this one into the, short, 3 minutes. How to integrate this one into the TRP? We have the microgrid concept. The microgrid concept here, we have to use the waste gas turbine to generate energy. You have to put a battery, a PV, and we have to integrate it with the power converter, and the power converter must be seamlessly integrated with these renewable energies. So this is the final proposal one. As we can see that electric arc furnace power supply, electrolyzer power supply should work in a harmony and also integrated together to enable for smart energy management system, enable for advanced models to be run onto that system. And this is the references. Thank you so much.
We have some 2 minutes for questions. Thank you.
Consider PEM technology over as compared to other technology for your context.
I didn't check. I just use the PEM technology because we have that one in our plant. But I don't have any difference now between the PEM and that. But I think the PEM one is emerging for maybe for the fast response.
Okay, thank you.
Yeah.
Thank you. No more questions? Okay, we thank again Dr. Hamed
Thank you.
for his very interesting presentation.
Thank you.
Thank you very much, Dr. Fernando ACTIS and distinguished speakers. I think this is a mistake on my part because we should make sure that all those speakers, we have got a little reminder, memento for them as a thank you, but we forgot to give it to them. But I will make sure that they get it before they leave. So now we reach nearly the apex of today's program. And before you leave, I would really like to get to the bottom of all the discussions and presentations that we have had today. We have put together a very nice panel discussion. I would like to invite my fellow panelists on the stage so that we can finally wrap up the day. The title of this panel discussion is Strategic Pathways for the Transition Technologies. So the panelists are Dr. Alexander FLEISCHANDERL, Primetals Technologies, Dr. Fernando ACTIS from Ternium, and Dr. I do apologize, I will only say the surname, Dr. Shin from Posco. So please join me on the stage. Okay. So reflecting back on the first session of today, we talked about how the steel industry is making the transition towards becoming more and more green. So tomorrow probably we will go a bit more towards the breakthrough and more forward-looking technologies, but we should not forget on the way of getting there that the world is not uniformly blessed with all those right conditions that have to be in place until we make that jump or the switch. So this is why, while putting the program, I was helped by my fantastic scientific committee that we got selected from the technology committee, and they really helped shape that whole program there. So before we conclude today, I would really like to go through those details that we have heard from today. How, using the existing technologies, we can still make that gradual path away from the use of carbon. So trying to be a bit more efficient with the use of carbon that we do, trying to keep it a bit more into the perpetual motion, as well as trying to use the new fuels like hydrogen or biofuels in the existing technologies. So I would really like to explore, try to find out a bit more beyond what was presented in those presentations there. So people would really be interested in trying to see what you think, how the world is going to go in a certain direction. So I've put together a certain set of questions. I will go through them one by one. So depending on who feels like, please don't hesitate to jump in there. So the first area that I would like to cover is the use of alternative fuels in the existing technologies. The existing technologies, they have been perfected to such an extent that we have achieved a certain level of excellence there. Yes, we know that we cannot really squeeze out any more efficiency from them, but the way they work fantastic. So how do we make sure that these technologies can really still deliver us the decarbonization if we start switching the fuel a bit? So how do you see the use of alternative fuels? For example, the biochar, the syngas, in reducing the CO2.
Okay, firstly, I'd like to say that the hydrogen reached the gas, such as the natural gas, and also that the export gas from the steelworks. This is also good for fuel and also reductant. Now that hydrogen-rich gas is injected to blast furnace, then it definitely lowered the CO2 emission amount. And also that for using the biochar or biocarbon, this is also important. But the point is that the quality of biocarbon and biochar is important. How to get the qualified material is the important one. So, and according to the carbonization degree, the effect is very changed. So I think that quality control of that biochar is important for using that one, and maybe by using the hydrogen-rich natural gas for the iron making or steel making, it will be helpful for reduction of CO2 emission. I'm thinking that way.
Thank you. Any comments on the use of, let's say, biochar or other alternative fuels?
I have a comment regarding biomaterials, biofuels, and biochar. In Ternium, we think that we have to work closely with the suppliers because it's a new value chain for us. And also, these natural materials are, in their essence, their quality varies a lot from time to time. The availability sometimes is variable. And so we need intermediate processes that help us to have a supply according to our industrial needs. So we can adjust the quality of what we are receiving through different treatment, thermal treatments, chemical conversion, drying, so that our processes, the blast furnace, the direct reduction modules, will receive more or less almost a constant quality of biomaterials that will be useful. We know they work, but to have an industrial supply is quite a challenge for us.
So you would say the scale and the variability are two important components.
Yeah.
And probably I would add one other one into that, the certification there, because you want it to be coming from some sustainable sources as well.
Totally agree. Sure.
Yeah, maybe to add on that, I fully agree. Scaling will be an issue. So it's a viable route, working with biomaterials to replace fossil carbon, but it cannot be the single route at the end. It can never scale to make decarbonization for the steel industry happen. It can be a minor share, supportive, can be also syngas from any biomaterial waste in gasification to be used. Even gasification of municipal solid waste might be an option to produce syngas to be used instead of producing heat from municipal waste. But anyhow, this will remain a minor pathway on the way to decarbonize the steel sector, I believe.
Right. So we are talking about the different pathways and techniques of decarbonization. And there are a number of those that you will find being talked about at different forums. Like, for example, here at the Breakthrough Technology, we had quite a number of presentations there. There was a debate this morning, or probably this afternoon, about CCS or CCUS. Do you think that it will diffuse enough into practice? Because the technology works. We just heard there from the example highlighted by Emirates Steel that the carbon capture and storage does work. It does have got an energy penalty that you have to clean the gases and the pressurization of that when you're pumping it into the ground. So the technology does work, but why do you think we don't see it expanding more into use? And do you think that going forward, that it is going to have some kind of a competition? Let's say now the technologies that we are working on, the breakthrough technologies, they require a certain amount of energy, the green energy. If that becomes available, that we are going to start talking less about carbon capture and storage. But if the pressure keeps mounting and we do not come up with the phenomenal amount of energy, green energy that is required there, then of course then people will start talking more about carbon capture and storage. And then we should definitely see more CCS being employed there. So which way do you think is going to go out of these two ways?
Yeah, let me kick this off, Rishan. So I would say, first of all, it's still an early stage on carbon capture and sequestration before we come to utilization. But it's, as usual, always the business case, I would say. As it is still an early phase, capital costs are still significant on all these technologies for carbon capture. For sure, the capex will come down. The more we multiply these technologies, we see it will stepwise come down with the capex. We see also significant improvements on the absorption liquids with higher efficiencies and less degradation. So that will help a lot. But if we say where do we stand now, well, depending on various technologies, but we still talk around maybe $50 per ton of CO2 for the captured carbon. And then you have to compress it and pipe it, and you pay the gate toll fee for the sequestration. So at the end, depending on the region, but we end up at maybe $70 per ton of CO2. So why does it not happen more frequently? Simply because the price of CO2 is obviously too low, or other way around, CCS the cost is still too high. So it does not match yet. But in the future, definitely, and all the reports are saying that carbon capture, sequestration, and utilization will play a significant role and will help all the heavy industry, I would say, threefold if we talk about steel. The first one is to produce blue hydrogen with CCS. The other way is to place carbon capture at blast furnaces, and the third pathway together with any direct reduction technology. So this will be hundreds of millions of tons of CO2 we will see in 1 or 2 decades. Yeah.
Thank you.
In our vision, we have many years capturing and using carbon, and we see that this is reaching a plateau because the offer is growing and will grow very much in the next years, but the demand is not growing enough for these traditional uses for beverages. And so the pressure for storage is increasing, but in the countries where we operate, there are no incentives up to now for storage of CO2, and Alexander mentioned the cost is still very high. So I think we have to wait a little bit more for our societies to mature these ideas that we need to do it.
Okay, I'm of opinion that CCU is more preferable for us rather than CCS because the carbon is a very elementary material for the human life. But the massive CO2 sequestration can be achieved by CCS. That's the point. So but the point is that for the CCS, we need some storage area place. But the storage place is not evenly distributed all over the world. It is concentrated in the, in kind of the natural well, natural gas well or oil well or something like that. So especially the Korea and Japan has no the sufficient area for the carbon CCS. So that I am of opinion cross-border CCS is important for the expanding the use of CCS all over the world. Yeah.
And I keep touching that point, and I've checked the temperature a few times in the past 3, 4, 5 years, and the situation has not changed. So I do not see any disagreement about CCS, at least, that the conditions are still the same that were being said a year back, 2, 3, 4, 5 years back. It's about the cost, it's about the perception. So it is still the same. It's kind of a stagnant position there, but there seems to be some kind of a disagreement about the CCUS. We heard an example from LanzaTech that there are some uses for capturing carbon, but again, you highlighted there that there are certain regions of the world where you have to find a proper business case. Because at the end of the day, even if you if you produce chemicals, if you have to use an alternative source of carbon over there, why would you do that? Why would you still use the fossilized form of carbon there for producing chemicals or anything else while you already have got access to carbon? So why not use it there? But there are certain markets, it doesn't make a proper case there. But in certain markets, it does. So there are some regional differences in the CCUS at least.
Yeah, shall I take it from here? So first of all, I don't know if the audience is aware, but if we talk about different regions and the capacity to store CO2, it's about 2/3 of the world's capacity explored is in the United States. So therefore, I believe United States will be the first mover, really, with big capacity on sequestration in their hubs, especially to the south in Texas offshore. These are developed. Well, if we talk about other places, like in Europe, it's simply the society still not accepting in many countries in the European territory to allow for sequestration. Just take Germany as an example. This was quite a strict debate, and it's even now positioned as a law, not allowed to be sequestrated. That's likely going to change because it might be the only alternative to keep the pace in the decarbonization for the hard-to-abate industry. But it's still not ready. And there have been, just taking another example, like in the Netherlands, I don't know if someone from Tata IJmuiden is here from the Netherlands, but they, if I remember correctly, they targeted first to apply for carbon capture and to sequestrate the CO2, but found no support from the local people, and finally they lost the support from the government. So they had to leave this pathway, and the only way forward is now with hydrogen. So in Europe it's still difficult, except a few places like in Norway or in the UK. So that's main reasons.
So I would like to now explore a bit your brains about the transformation of existing assets to be able to use the new energy sources, for example, hydrogen. So we see quite a number of projects that have been trying to replace the use of natural gas by increasing percentage of hydrogen gradually, and then claiming that, yeah, we can use up to 100% of hydrogen in there. So do you think that there is a possibility that we will see the transformation of all the existing technologies which were using hydrogen, that they can replace it entirely, all of the natural gas that was being used?
Well, I can give an example. I showed it this morning. Our new plant that is going to be built in Monterrey will start operating with natural gas because it's what we have. But when hydrogen becomes available, the plant will be ready to switch. It's a question of availability, not of technology for us.
So do you think that all of those questions or challenges have been overcome, which we used to hear, and I have still heard them, that hydrogen reaction is quite a fast one. You immediately get the reduction on the outer layers, but inside it still stays the same.
Yes, that's something that Tenova people should explain better than me, and they are over here, but we have the experience and the certainty to move forward.
Okay.
Okay, so changing the reduction gas from carbon content gas to pure hydrogen, you know that everybody say that all the process is ready for transition to hydrogen, but we are also targeting to pure hydrogen-based iron making process based on crude ice bed. But with studying the hydrogen phenomena in the reduction, we finding new ones every day. So that's I think there will be some technical barriers still existing, and we should overcome that one. But I think that it can be treated and it can be overcome. But the point is it's how to get the green hydrogen or low CO2 hydrogen. How can secure the sufficient of amount of hydrogen? This is the main factors, especially the green power and the green energy is not even it is distributed over the world. It is concentrated. That's very windy region and sunny region, so that how to secure the sufficient amount of hydrogen, that is most important one. And we are trying to import the hydrogen from the hydrogen-rich area, but transportation has some big challenge for the hydrogen, the securing. So maybe for substituting to the green hydrogen, we are thinking about it using our own the resources such as atomic power or direct pyrolysis of CH4. This is also under consideration. So that's, in my opinion, the hydrogen, the problems in the hydrogen reduction, the process can be, there is some challenge, but it can overcome. But the important one is how to secure the sufficient amount of hydrogen for reducing the CO2 emission. That is the important one for me.
I take your point, and I would not like to step into or compromise the discussions in the second panel. I would not like to make anybody angry, because we are stepping into that territory. That discussion is going to talk exclusively about the breakthrough technologies. So we have come to the hydrogen and the use of it in the existing technologies, or at least the transformation of those technologies to use more and more hydrogen. So you highlighted a few bottlenecks there. For example, there are concerns there that we will have the technologies and they will be perfected sooner or later. But the worry is that we will not have enough hydrogen to use in there. So everybody is aware of those challenges there. And I agree with you. I am more hopeful for our progress, or at least our sincerity and our efforts, that they are going to be fruitful quite soon. So in a situation like this, where you have got the perfection in the technologies, but the lack of the right raw materials or the energies, as Alex, you highlighted this morning, there were two key areas. One of them being the raw material, because most of the existing technologies are targeting only the higher end of the raw materials, because it's easy. You can quickly realize those projects there. But the 80 to 90% of the spectrum of the iron ores which are available there, the new technologies, they're still being developed there. And there are quite some challenges there. So one of the bottlenecks is the raw materials, that we need to start working for those, for that raw material as well. The second one is the availability of energy. And paradoxically, the lower the iron ore quality, the higher the energy input.
Yeah, would agree with both things you mentioned, Rishwan. So I just would put it in a different order. As I said in the morning, I think the major roadblock is the energy availability and pricing. And the other one is then about the feedstock discussion. Anyhow, well, technology is there for direct reduction on high quality iron ore and running on natural gas. Well proven and works, including carbon capture or without, does not matter. Well, what is not completely de-risked and commercialized is running on low-grade iron ores and all the related topics. Well, on a paper we can say direct reduction works with any iron ore grade. So the direct reduction itself will work with hydrogen, with the syngas from natural gas, but they're related problems. Yeah? So just taking blast furnace pellets are not so strong than the acrylic pellets. So you have more fines and have an impact in the process and availability. And on the other hand, well, we have to question ourselves, is it really the target? As you said, well, can we run on 100% hydrogen? I would say finally, yes. So this has been proven at least at smaller scale, and likely we are going to see it in one of the major projects over the next years. But I doubt that 100% hydrogen is really required and does make sense. So steel requires carbon. The EAF likes and loves to have a certain carbon content. So I would say the ultimate target might be to run it 80–90% hydrogen, but not 100%, still producing DRI, HBI at minimum 1% of carbon for the electric arc furnaces. And when we talk about the lower grade iron ores and the smelter technologies, well, there are a couple of things that are still not fully developed, like, well, we produce high amount of slag from this process. And finally, we have not just to talk about decarbonization, but also about circularity. So it means we have to qualify these slags that they find their way into the cement industry or any other value-add application. And we say these slags are similar to blast furnace sands, true, but still it's a process to qualify these slags for the cement industry. And we have to have new standards for these slags to close the loop and utilize these slags again and have a circular economy.
That's an important point there. Anybody would like to add in there?
Just a brief comment about the iron ores of low grade. I think that in the next years we will see more and more involvement of the iron ore suppliers, as we have some of them here, just to condition the iron ores that we can find in every region to be able to supply the new needs of the transformed processes, maybe with added value through briquetting, through thermal treatment, and many other ways to adjust the quality to what will be needed.
So, Alex, I would like to challenge that comment that you made there, that if the slag made by hydrogen-based processes is at par with the blast furnace route, why would there be even a question to start to qualify it, that it is comparable to that? Because if you were to go to a clinker maker, you want to substitute, because the cement industry, in contrast to the steel industry, does not have any solution how to decarbonize. So they would kiss you on your hand and say that, please, how much do you have to sell us? Because that is the green input for them. So why do you think we will struggle?
No, it's not what I've said that we struggle, but still there are cement clinker standards. And these new type of slags are not within the existing standards. I believe this issue can be solved. It's again, and we talked this morning also about partnerships, and I think this is also a quite important cross-industry partnership that is required to have close ties with the cement sector to provide, as soon as the first prototypes are running and this slag is produced, to supply these slags to the cement industry and to let these guys do their work to qualify these slags, to include it into this or amend the standards, and simply then to supply the slags to the cement industry. Yeah? So I agree, but at the end, kissing from the cement industry won't be enough. So there has also, this comes with a price tag. Yeah?
Yeah, exactly, because this is coming as a green input to their process, so they would love it. But I also agree with this, that there has to be some kind of a collaborative effort then together with the cement industry to try to find a way that we can make sure that they qualify, fulfill a certain physical characteristics that they're looking for.
Okay, so, but you know, for the cement plant, the blast furnace slag is very good for their decarbonization, and you know that. But if we go for the hydrogen reduction based on the electric arc furnace, we cannot produce such a high quality of the slag for their use. So that we alternatively we can go for another route to produce the similar quality of slag to blast furnace. So that we are looking for now, and we are studying that how to get such a qualified slag for the cement plant. That is our one target of our process development.
So that's an important point that you raised there, and I would take that as a cue to highlight the project or proposal that Edwin mentioned this morning, and Mr. Choi also mentioned, that we as World Steel is working on. We would like the steel industry or the interested members to join that research proposal, which is exactly trying to remove these obstacles in the use of hydrogen. So it is not developing any new technology, but rather trying to find answers to these kind of tricky questions. How do we make sure that the slag produced is comparable to the blast furnace slag, that it can supplement or substitute? The other one is hydrogen storage at a scale, and to find the answers to the high gang content also, because the higher the gang, the higher the energy penalty. So 3, 4, 5, these nice topics, which do not really compromise any technology, but they do cut across and affect all of the hydrogen-based reduction technologies. So that's the process that we are working on, trying to find a way for the steel industry to really move a bit forward at a faster pace.
Okay, I agree that the many steelmakers have the common question and the common task for the future, so we can make take out some subject for the collaboration for the R&D for the future. I agree with you.
So I think we have reached the end of today. I thank you very much for all my panelists. If anybody would like to ask any question before we wrap it up, please, can we have a microphone? Yeah. Second row. For the ladies there? Oh, yeah.
Okay, thank you so much for the opportunity. I would like to ask about the carbon capture technology. Now, in Emirates Steel, we are using it in enhanced oil recovery. Okay, so for example, science-based target does not recognize that as a method for the carbon offsets. So can you please give your opinion on that?
Anybody?
Yeah, so I can provide my opinion on that. Well, I think still it's a viable option, yeah? Even if it's not recognized on the science-based targets. But it's anyhow a use case where finally the CO2 is sequestrated and used. But it's likely the worst or the less best solution on sequestration. So better would be any different utilization, like transforming the CO2 in any chemical product or into plastic finally, where it's locked in the product for second life of the CO2. Unfortunately, this is not so advanced yet, so there remains the routes to go into fertilizer. I think that's a viable option today, to produce fertilizer from the captured CO2, or enhanced oil recovery will remain a solution.
But we're not ready yet for phasing out fossil fuels, because we don't have developed alternatives. So we need fossil fuel. Okay, we cannot phase it out. That's one. Second, plastic has many other issues. Many of this produced plastic is non-biodegradable, right? Okay, and it creates another problem to the environment. So should this be at least a temporary solution till the technology is being developed?
Yeah, I think that that could become a long discussion. True that plastic comes with many other issues, but I think it's obvious that we won't get out of plastic over the next decades. It's a quite important product in the value chain. And the best solution is still to produce any plastic from the CO2 and not from fossil fuel, and partly replace it. So I think it's a viable option. It really helps. And all the problems with wasted plastics is a topic, I think, not addressable now to the steel sector, but I fully agree that it is an issue to be solved. Yeah.
Okay, so the blast furnace is very good reactor for decompose of plastics because it's a high temperature inside of the furnace. But the limitation for using the plastic is that how to qualify the plastics. You know, the plastic has many contaminants such as steel and another and many things to be bad for the atmosphere. So that how to classify the plastic. This is things to be solved in advance to use in the blast furnace or something like that.
Yeah, probably this is the issue of circularity, that anything that helps with the reduction of digging more fossilized fuel, be it gas, be it oil, or be it coal, by any type of efforts. So, for example, if you use carbon in chemical processes, in producing chemicals, if you would have to dig up more carbon for that, and if you could stop that by using carbon, which is already in this loop, that means that you are filling the existing carbon into the environment with a lower amount. So again, I agree with you, it will become quite a long debate there. Any other question?
I would like to ask something about the hydrogen and using that for steel industry. My question actually regards the issue of hydrogen leakage or hydrogen emission. And recent publications show that the global warming potential of hydrogen is around 12 times higher than CO2. And if we move towards a hydrogen future, and if we have around only 10% leakage during the transportation phase, using hydrogen will lose its point altogether. So I just want to know what's your opinion about that, and do you think it could be a major obstacle for using hydrogen in the steel industry? Thank you.
I could not localize where the voice was coming from, sorry, but I think one viable option could be on ammonia. Yeah? Ammonia is much easier to ship, don't need this high compression than liquid hydrogen shipment. And the charming thing about producing iron with ammonia is that you can avoid to invest into ammonia cracking. Yeah? So if you feed ammonia, it's still not exploded and finally developed, but you can inject ammonia into the direct reduction, because the fine iron, metallized iron particles serve as a catalyst. You have the temperature level, you decompose in situ in the process, and that might become an option, but will take a couple of years more.
Direct use of ammonia for DR plant, this is not a good way. You know, it can reduce the reduction temperature to lower degree, but you know that some nitrogen is dissolved in the DRI. That makes some problem in the future. So I'm of opinion the ammonia should be cracked in advance to use for the DR plant. I'm thinking in that way.
Okay. My name is Kim from Posco. My question is going to Alex. I remember during your presentation you mentioned about the decoupling of the iron making, steel making, and then I understand the background of that. And I think you know the ammonia and hydrogen, they've got kind of you know transportation issue. Yeah. So I think that's why you mentioned that. But I think there might be some I mean pros and cons. Yeah, in every you know theory and so decoupling is really happening. I mean, if we have the kind of industry changes, yeah, what will be pros and cons in that decoupling?
Well, I think that's a very political question at the end, and has also to be decided by the government. Yeah? So if we take Europe and we want to remain the full value chain, iron making and steel making, it requires strong support from the public side, not only for the capex, but also closing the gap in the operational cost due to the high energy prices. And pretty sure that it's not going to change over the next few years. Yeah. So, and the question will be, how long will the governments be able to support to close the gap on the energy prices? So you can take this as an advantage or disadvantage. Advantage is, well, the workforces remain in place. You have the full value chain. On the other hand, you take a lot of public money, which is a disadvantage. So if you decouple iron making and steel making, you lose a certain part of the value chain, and has an impact also on the employment rate in the steel sector. No doubt is a sensitive topic, very touchy. Huh? But on the other hand, it might secure on the long run to keep the steel sector alive on the more downstream side. And that's really the differentiating factor, right? Work on development of new high-strength steel grades, fully integrated with the other sectors, the automotive, the building, the white goods. And that's important, I believe, and not only for Europe, I guess also for Asia. Yeah.
Thank you very much. So we reach the end. We have crossed 15 minutes mark. I would not allow more than that, taking too much of your time. I hope you have enjoyed the day like I did. I mean, I can't make that claim. You will have to tell me probably at the dinner when we meet again. So before we leave, I would just like to make a few announcements there about the bus timings. There will be buses leaving from here, going for the dinner. So I would ask my colleagues to please take the mic. Sylvia, if you can please tell us when the buses are leaving.
Yes, so for the dinner, the buses are leaving from the Intercontinental Hotel as 6:30, so 6:30. But we have also bus for the participants who are staying at the Rixos Marina, and that bus is leaving at 5:30.
So the first bus leaves 5:30 for those people who are staying at Rixos, and for those who are at the Intercontinental, the bus will leave 6:30. So I look forward to seeing you at the dinner. Thank you very much.